The position vectors of points P and Q relative to the origin O are 4i plus 2j and ki plus 4j respectively. Given that QP is perpendicular to OP, find the value of k. Okay, so when two or more vectors, or let's just say when two vectors are perpendicular, then their dot product is always a 0, and the reason is very simple, because the dot product of two vectors is defined as AB is equal to the magnitude of A multiplied by the magnitude of B multiplied by cos theta, where theta is the angle between the two vectors. So if the two vectors are perpendicular to each other, then this angle here is 90 degrees. So that means when two vectors are perpendicular to each other, then remember that cos 90 degrees is 0. So it follows that when you multiply 0 by these numbers, you get a 0. So this is what we shall take advantage of to solve for k. So we have the first vector here, which is 4i plus 2j. Actually, we are told that the vectors which are perpendicular to each other are QP and OP, these two here. So now we can start by finding our QP. So remember, QP is QO plus OP. So our QO is, so they started with P, so our QO should be this one here, of course with a negative sign since we have changed the direction. So Ki plus 4j, and then plus our OP is 4i plus 2j. So now we can simplify this. This will be minus Ki minus 4j plus 4i plus 2j. And then putting the k terms together, this will be minus Ki plus 4i, and then minus, this and this will give us minus 2j. Then we can factor the I out and say we have this minus 2j. So now this is perpendicular to OP, and then OP, from here we can see that our OP is the first one. This is 4i plus 2j. So that means QP multiplied by OP is 0, the dot product. So our QP is this one here, so minus K plus 4, or let me just put it like this, 4 minus Ki, that's this one, and then minus 2j multiplied by our OP, which is 4i plus 2j. And because they are perpendicular to each other, we can equate this to 0. And then remember, when you are multiplying vectors, you multiply the i's by the i's, the j's by the j's. So this by this, we have 4 minus k, and then this by this, we have minus 4. Then we can expand. This one will be 16, this will be minus 4k, and this will be 4 is 0. Then this minus this is 12, minus 4k is 0. We can take the minus 12, the 12 to the other side, so that we have this. Divide both sides by minus 4, and your k is 3, and you're done. So it was easy. Let's look at part B. two lines R1 and R2 intersect at R, and then R1 passes through the point with position vector this and that. Given that R2 is this, find the coordinates of R. Okay, so just like in coordinate geometry, to find the point of intersection of two or more points, you have to solve the two equations simultaneously. So in this case, we have R1, this one has been given, R2, this is I minus 3j, then plus lambda I plus 2j, and then we are told that R2 passes through the point with position vectors, these two here. So if I was to call this one A and this one B, so our job here is to find the second equation, which is R1. Once you find this equation, you can solve it simultaneously with this to find the coordinates of R. So let's do that. So to find the equation of R, you need the direction. Remember, the direction is more like the gradient, and then you need 1 point on R. So you can either pick this or this. Whichever you pick, despite the fact that the answers may look a bit different or equations may look a bit different, they are technically the same depending on the value of k you find. So let's say we want to find the equation of R1. This will be given by A, 1 point on A, one vector along A, and then B will be the direction. Of course, I can't use the lambda because it was used, so in this case I'll use me. This one is me in Greek. Others will just say it's mu, but the Greek pronunciation is me. So you may hear me call it mu, you may hear me call it mu, you may hear me call it me. In most cases, I go with the original pronunciation. So we have A plus me and then B, where B is the direction vector. So we can start by finding B. So this B, if we were to call this one AB, then B will be the direction vector of A and B. So we can just break this one down to AO bar and then plus OB bar, and then our AO will be this in the other direction. So 5I plus 3j, and then plus OB will be this one here, minus 2I minus 4j. So now we can simplify this. So this would be negative 5I, negative 3j, minus 2I, minus 4j. Items together, this and this, we have minus 7I. This and this, we have another minus 7j. So this will be your direction. Another one can factor out the minus 7 and say the direction is this. So this is still correct. It's actually better and much easier to use, but this can do the job just fine. So now let's find the equation. So the equation will be R is equal to A, which is any point on AB. So I'll go with this one. I don't want to have too much of negative numbers since I have a choice here. So minus 3j, then plus me, and then B will be the direction. So you can either use this or this. So I think I'll go with this one. If you want, you can try to use this and you realize that the answers will still be the same. Since this is a scalar multiple of this, it means the two vectors are in the same direction. In other words, this and this are in the same directions. It's more like 4 over 6 and 2 over 3. So this is exactly the same as this, except that this is much better to use because it has been reduced. Another explanation here would be the gradient is y over x. So like y1 minus 0, but forget about the zeros, just get the coefficient of this over this. This will be a 1. And then when you use this, you use minus 7 over minus 7, you still get a 1. So either ways, you still have the same answer. So now we have two equations. We have this equation and the equation we have been given. So we want to solve them simultaneously now to find the value of, to find the coordinates of R, which is the point of intersection of the two vectors. So now let's solve the two vectors simultaneously. So to solve these two vectors simultaneously, you can just substitute this there. I know it's kind of weird because this is R1, but where there is R2, you are putting R1. So this is how vectors are solved simultaneously. So 5i, in short, where R1 is the same as R2. I think that's the best explanation I can give. So this is why we do this. This is the only time when R1 is equal to R2. It is at the meeting point. So now let's simplify this, put the I components on one side and then the J components on the other side, and solve for the unknown. Find the value of lambda or the value of mu. You just need one. Whichever you pick, you should have the same answer. So we have this plus 3j. Let me expand this. This will be mi I, and then this will be mi j. And then we have I minus 3j plus lambda I plus 2 lambda j. And then putting the items together, and then here we have 3j plus mi j, and then we have I plus lambda I minus 3j plus 2 lambda j. And then we can factor the I out and say 5 plus mi I. Then this side we have 3 plus mi j is 1 plus lambda I. And then this side, let's just say 2, I'm starting with this one, 2 lambda minus 3j, like this. And then now that we have the I components here and the I components here, the J components here and the J components here, we can compare and equate. So we have 5 plus mi, this must be the same as 1 plus lambda. And then the other equation here is this 3 plus mi is 2 lambda minus 3. So now to solve this, we can simply, I think I'll just take this one to the other side. The choice is all yours. This minus this will be 4 plus mi is lambda. And then I'll do the same thing here. I think we should have made me the subject here. It's much easier. So you can just take this one to the other side. And then we can make me the subject of the formula here too. You take this one to the other side. You have mi is 2 lambda minus 6. and then now you can equate this to that to solve for lambda. If you want to solve for me, you can just make lambda the subject of the formula. You don't need both, by the way. Maybe you can find both just to verify your answer. So I'll substitute this one there so that we have this one there. Me minus 4 is 2 lambda minus 6. I'll take the 6 to the other side and the lambda to the other side, so that we have 2 is equal to lambda. So this is your lambda. If you want to find your me, you can also find it, but it's not necessary. 1 is enough. So your me will be negative 2. So now to find the coordinates of r, you have the two equations. You have this equation, and where is the other? Okay, we have these two equations here. So if I want to find the coordinates of r using the first equation, I can simply say r1 is 5i plus 3j plus my me is minus 2. So this one will be minus 2i plus j. So r1 will be, let's expand 3j this and this minus 2i this and this minus 2j. Then r1 will be this minus this, which is 3i, this minus this is j. So these are the coordinates for r. This is the vector. So to find the coordinates, you can just get these two. This is like the position vector of r. So the coordinates will be 3, 1. If you want, you can use your lambda and the other equation which has a lambda on it. So if you decide to do that, then your r2 will be I minus 3j plus, where you have your lambda, just put your 2. So you have 2, and then you have I plus 2j. And then let's simplify this and check if we are getting the same answer. As a student, I was using this to verify if my answer is correct or not. So we have this. So now this and this will give us 3i. Then this and this will give us j. So as you can see, this is the same as this. And if you decide to get the coordinates for r, you have 3, 1, and you're done.